Good morning, sir.
Good morning. Good morning.
Morning, sir.
Good morning.
Good morning, sir.
Good morning. Give me a moment. Let me open the slides. Have you received the assignments I have posted in the Google Classroom? I have posted assignment in the Google Classroom. You solve those questions only.
Yes, sir.
It's more than sufficient from the internals point of view. Okay, we are left with engineering constants theory and problems. Let us go ahead and solve those. We will define few engineering constants. So we already know. Let me define once again. First is Young's modulus. Young's modulus E. It is given by the ratio of linear stress to linear strain within proportionality limit is equal to Young's modulus. That is sigma Young's modulus times epsilon. Sigma by epsilon is equal to Young's modulus. Second, Poisson's ratio. Nu or mu or 1 by u. The ratio of lateral strain to linear strain within proportionality limit is constant given by nu is equal to epsilon lateral by epsilon linear longitudinal. Similarly, a few more constants. Modulus of rigidity, modulus of rigidity. It is analogous to Young's modulus C. When the shear stresses are applied, we will be getting this modulus of rigidity. So I can define the ratio of shear stress to shear strain within proportionality limit is a constant for a given material called as rigidity modulus or modulus of rigidity called as modulus of rigidity. It can be written as tau is equal to g times gamma or tau by gamma is equal to g. Shear stress is directly proportional to shear strain. When I remove the constant of proportionality, I'll be getting this rigidity modulus G or modulus of rigidity. The next constant is bulk modulus. Let us consider a cube like this. Let us assume that it is immersed in water. It is immersed in water. I am just writing like this. When it is immersed in water, it is subjected to equal forces. Equal force in the sense it is subjected to P like this. P instead of P, I will be writing sigma. Since sigma is equal to P by A, I can write instead of P, I can write it. I can substitute it by sigma. It is subjected to equal normal stresses, sigma like this in all direction, isn't it? It is subjected to stresses, same stresses, compressive stresses in all direction, sigma, sigma, sigma. Okay. Now, this bulk modulus is given by K. Bulk modulus, it is the ratio of to the ratio of direct stress, or I can write ratio of. See, once if I when I apply this type of loading, when the body is subjected to normal stresses, always there is a change of volume. There is no change of shape. So I can say it is the ratio of direct stress to volumetric strain. It is the ratio of direct stress to volumetric strain. I can write K is equal to sigma by epsilon. It's the ratio of direct stress. Three mutually perpendicular axes. There's a direct stress acting. We can write it is the ratio of direct stress to volumetric strain. Okay. This is bulk modulus. I will read out the statement. The ratio of direct stress to the corresponding volumetric strain is found to be constant for a given material when the deformation is within the certain limit, it is within the elastic limit. This ratio is known as bulk modulus, that you can go through yourself. Okay. Now we will derive an important relationship between, this is generally asked in the examination. I also, this has been asked in the internals also, one of the question paper. See, let us consider, let me call this as generally asked for 10 marks, relationship between E, Young's modulus E, Poisson's distribution U, and the rigidity modulus G. Okay. Now let us consider a cube like this. Consider a cube like this, and it's a square cross section. All the sides are of length A. This is also A, but sorry, all these sides are of length A, whereas the thickness is of 1 mm, 1 unit. Either it can be 1 mm, 1 meter, 1 kilometer, whatever. It's 1 unit, and right thickness as 1 unit, 1. Okay. Now, if I let us assume I'm applying a shear stress like this, shear stress on this surface. I'm applying a shear stress on this surface like this. I'll call this as tau. I apply the shear stress on the surface. I'll call this as tau. When I apply a shear stress on this surface, for equilibrium, let us consider 2D of this. Okay. Before that, okay, if I consider in 2 dimension only the front plane, if this tau is given by tau is equal to F by A, or tau into A is equal to F. I can replace this shear stress by force by multiplying shear stress by force, isn't it? I know tau, this area is given by this A into 1. Tau into A into 1 is equal to F. I'll replace this shear stress on this face by tau into A into 1, or F is equal to tau into A only, or tau into A, or tau, you can call it as, I will write it tau into A. This is acting like this. So this is the shear force acting on this face. Now for equilibrium, if this is the shear stress acting, let me call this as figure A, figure B. For equilibrium, that is, if this is shear stress tau into A acting like this, for equilibrium, there should be an opposite force tau into A acting in the opposite direction. Isn't it? The reaction, this is the reaction force. This is the actual force we have applied. The reaction force tau into A should act opposite in the opposite sense, so that this force cancel out. But due to this, even though summation of forces is equal to 0 in this case, summation of forces in x direction is equal to 0, but summation of moment is not equal to 0. It leads to clockwise moment. It leads to clockwise. See, you try to, it is rotating the this our so this plane in the clockwise direction. In order to avoid that, for equilibrium, for equilibrium, tau into A, tau into A, there should be another shear stress acting in the opposite stance. Another in the opposite plane, there should be shear stress of equal magnitude acting. This leads to clockwise movement. This leads to clockwise. This and this leads to clockwise movement. Whereas this and this leads to anti-clockwise movement. Therefore, in this case, summation of forces is equal to 0. Summation of moments is equal to 0 at any point you can take. So, what we can deduce from this is shear stresses are complementary. Even though I am applying shear force on one of the plane like this, on this edge, or one of the plane like this, but due to this, I am getting shear stress. This is the reaction force. This is on the this plane. If I call A, B, C, D, I am applying shear stress on this plane. This plane. This shear stress on the other plane. There is due to this one shear stress, I am getting another set of shear stress, isn't it? Hence, the shear stresses are complementary. Due to one set of shear stress, I am getting one more shear stresses. Therefore, I can say that shear stresses are complementary. Complementary is in the sense, if you go to a shop, you take one thing, they will give one more thing. So, sir, this is the complementary we are giving. Similarly, this holds good for shear stresses also. Even though shear stress is acting on one of the plane, for equilibrium, there should be shear stress on the another plane also. This is known as complementary theory of shear stresses. I can write, if I write tau acting on AB plane, or I can say generally what they will do, they will call this as tau dash and they will do that. But if you have understood this, more than sufficient. Shear stresses are complementary. If there are shear stress acting on the one plane, you should understand that there is also shear stress induced in the other plane. For example, if the body is, if you fix us like this, if we apply a shear stress like this, if you apply shear stress like this, you should assume that it will deform like this. It will deform like this. There's shear stress like this. There's also shear stress like this. There's also shear stress like this. There's also shear stress like this. This is complementary. When it's acting on the one plane, it is induced on all other three planes, all other two planes. It's complementary. Okay. Next, keeping this in mind, we'll go ahead. Now, let us consider this parallelepiped. Now we know the shear stress. So if I call this as tau xy, I will when I come to the Mohr circle, I will tell you the same. Okay, this is tau. This is, if I call, this is opposite face like this. This like this. Okay. Now this is 1 unit. This is 1 unit. This is length A. This is also length A. Okay. Now I can replace this by, as we have done previously. If I take the front plane, I can replace this by tau into A, and tau into A. This is acting in this fashion. This is acting in this fashion. And then see, always this corner and then this corner should meet. If this is in this direction, these two corners should meet. That is, you should remember blindly. This the arrows should opposite to each other. It cannot be like this. This shear stress cannot be like this. This arrow should be like this. Okay. As soon as you write one arrow in the opposite direction, you should write other arrow, and then you should write other two arrows. Okay. Now, if I take, for example, if I take like this, let me write a section I am passing like this, right, like this. a section I'm passing this, even though it's thickness is less, assume that this is of 1 unit. I have passed the section, this is of 1 unit. Okay, we know that this is the force acting on this plane is tau into A. This is tau. This is tau into A. This is tau into A. Okay, this is 1 unit. Now if I take this as the right angle triangle like this in a 2 dimension, if I assume, if I take like right angle triangle, this is tau into A, this is tau into A. Okay, now for resolution of forces, this should be actually like this. This should be actually like this. This is the resultant. This is the resultant. This is tau A, tau A. But always you should remember that according to parallelogram law of forces, if two forces P and Q, this is P and Q, this is P, Q acting this fence, this resultant is given by diagonal passing to P and Q. This is the resultant. Similarly, I can write the resultant of this two tau A and this two tau A and tau A. The resultant should be passing through this. I will write the resultant as this. This is the resultant. Okay, this is the resultant. Now, what is the magnitude of resultant? According to this thing, Pythagoras theorem, I can write the resultant R. I can write this as R square, which is equal to R square, which is equal to tau square A square plus tau square A square, or R square is equal to 2 tau square A square, or R is equal to root 2 tau A. Root 2 tau A. This magnitude of R is equal to root 2 tau into A. Hope you are understanding this. Okay. This R is given by root 2 tau A. I have taken the magnitude. I have taken the resultant. If I take the resultant, I know this is given by Pythagoras theorem resultant root 2 tau square A square and tau square A square plus tau square A square, which is nothing but 2 tau square A square. R is equal to root 2 tau A. Okay. Now after knowing this, area of this. So what I want to convey is, if I apply the shear stress like this, shear stress like this as shown in figure A, always you should note that, this is the actual figure in 2D. This is the actual these are the diagonals. Let me call it as A B C D. When I apply the shear stresses, I'm not indicating the shear stresses here. When I apply the shear stresses, this will deform to the new position. And the new diagonal, I will call it as C dash D dash, C dash D dash. And if I drop a perpendicular from this point, This is perpendicular. I will call it as F. Okay. Now, see, what you should know is when I apply the shear stress like this, by visualization only you can see that AC dash is subjected to tension and BD dash is subjected to compression. This AC dash is under elongation and BD dash is under compression. If you stretch like this, if you imagine if you are stretching like this, your AC dash is under tension and your BD dash other diagonal is under compression. Okay, that should be your imagination. Okay, if I write now since I've taken uh, um this part, this if I call this part, this L-shaped section, this is under, if I write like this, let's write one more triangle. If I write like this, these are the diagonals. You can see this, the resultant force is acting away from the body. Resultant force is acting away from the body. This is the resultant which is acting like this. This is the section, if I call this as, yeah, whatever, this is ACB, whatever. This is the resultant which is acting away from this set. It is from this set, it is acting away like this resultant. Simply for equilibrium, there should be one more resultant which should be acting like this. This is resultant. Also, we can show that by visualization only, you can see that if I take the other edge, for example, if I take the other L shape like this is the second part. If I take like this, if I take this is like this, tau into A, tau into A like this, tau into A like this. For equilibrium, actually it should be like this and like this, tau into A, tau into A, tau into A, tau into A. And this is the resultant. This is the resultant. Okay. How it is acting? Okay. This is tau into A acting like this. This tau into A acting like this. Resultant is acting like this. So for this to be equilibrium, if you take this edge, if I take the other L shape, this will be under compression. This edge, if I take, this will be under compression. That is by visualization also. Or if you write, this is the resultant. Just give me a moment. Okay. This is under tension. This is pulling like this, pulling like this. This is like this. Okay. This is like this. This is acting like this. This is acting away. This is acting. Sorry. This is acting. The resultant is acting. You can think. You can think. You can work on your own. The resultant. Sorry. This resultant. The other diagonal. It is compressive. That you should remember. On one of the diagonal, that there is a tensile force, and the other diagonal there is a compressive force. Isn't it? Just by visualization also you can see, and just by solving also, the resultant is acting away from this. You take the resultant, this is the resultant like acting away, that is acting away. For this to be equilibrium, the other resultant should be in the opposite direction. Therefore, this diagonal, the AC dash is under tension. AC dash is in tension. Similarly, the diagonal BD dash is under compression. You can work out. Diagonal BD dash is under tension. Okay. Now the magnitude, let me come this, the area of this surface, where the resultant force is acting is given by, area is nothing but length is, this is A, this is A, area is nothing but, if I call, let's write that, this is A, This is a, forget about the thickness. Thickness is 1 unit. If I write like this, next hour also I will be engaging. I have to complete the questions for the internals. Let me complete up, or it will be very difficult for you to solve the problems. I'll complete it. Those are very simple problems. Once if I do, you will understand it. This is A. This is A. Assume that this is what I'm talking about. This is of 1 unit. 1 unit. Okay. If I write this is A and A, this is given by this is if I say O A B, this is AB is equal to 2A square. AB square is equal to 2A square, or AB is equal to root 2A. Root 2A area is given by root 2A into 1. Okay, this is the area. Now we know that the magnitude of shear force acting on uh, the edge. If I say, if I call this as magnitude of shear force acting on the diagonal is tau into it's root 2 tau. This is the magnitude of shear force acting on the diagonal. Okay. Now, if I divide this root 2 tau a, we know that. Let me give that. We know that if this is the shear force, shear force acting, root 2 tau is the shear force. If I divide root 2 tau a by area, that is the shear. I can write. We know that shear force by area is equal to shear stress, but I don't know the magnitude of shear stress. Let me write. Shear force is root 2 tau a by area we have found it now here. Area is root 2a. Therefore, shear stress. Therefore, the shear stress of magnitude tau is acting along the diagonals and on one of the diagonal it is tensile and the other it's compressive, magnitude remaining the same, tau. Hope you can understand. I have done the off part of it. What you should understand is from complementary theory of shear stresses, that is tau into A is the shear force. There is for another plane also there is tau into A shear force acting. Therefore, if I take the suction like this, and if I calculate if I evaluate the resultant, the resultant is of magnitude 2 times tau square A. This is the force acting. Now I want the shear force acting on that. If I divide it by the area of this section, which is nothing but this area is nothing but I can write AB square, which is equal to A square plus A square, which is nothing but 2A square, and in 2A square is the area. If I if I divide it by area, I will be getting the shear stress. I don't know the magnitude of shear stress, but we came to know that the diagonals are subjected to this resultant shear stress, nothing but On one of the diagonal, the shear stress is of magnitude tau expansion. On this diagonal, this is tensile tau. On this diagonal, this is tensile tau, tensile 2. Whereas on the diagonal, d dash c dash, this is tau compressive. Tau compressive. You can derive that. Okay. Since there's a constraint of time, I'm just rushing out. This is compressive. That's all you should remember. What you should remember, when a subject is shear, when body to shear stresses, on one of the diagonal it will be tensile shear stress of magnitude tau. On the other diagonal, there will be compressive shear stress induced of the same magnitude tau. Okay. Now there is a off part is done. Rest half of the part I have to solve it. I'll be solving it in the another. I'll be scheduling the class at 11:30. You please engage. We come to the class. We will finish it off. We will do this derivation, and 2 more derivations are left out. We'll complete it off. And after tomorrow, I will just be solving the problems. That is more than sufficient for the interviews. Okay. Have you understood this? Even though it looks complicated, but it is easy. You can understand by yourself. Have you understood this?
Yes, sir.
Right?
Sir.
Any difficulties? What I have done is I have taken the complementary shear stresses. I have taken the resultant. Resultant is of magnitude 2 times tau square A. Now, if I want to evaluate the shear force, I have to divide it by the area. Area is given by 2A square. If I divide it by the area, I will be getting the magnitude of the force. Magnitude of the force as the shear stress. The shear stress is of magnitude. The shear force, shear is nothing but force. Is of magnitude. This one tau. This is tensile. This tensile tau is acting on the one of the diagonal, and compressive tau is acting on the other diagonal. Okay. Now I'll wind up. Any doubts? Any doubts?
No, sir.
Any doubts?
Sir.
Okay, I'll continue at 11:30.